mid-latitude systems. We've come down from planetary to mid-latitude. Well, we're going to get down another scale uh, to thunderstorms. Each of us have dealt with thunderstorms at some time or another. They're a part of weather in the mid-latitudes and over the tropics and even over Alaska. There are thunderstorms at times. So, what are some of the factors that cause a thunderstorm? Why is that? Well, we talked about extratropical lows bringing rain and snow. Well, why do sometimes those extratropical blows bring lines of thunderstorms, severe weather? Well, let's look at a case study today. What's going on? Uh, we have a cold front that stretches from northern Missouri almost into Iowa, south through central Oklahoma. Along that cold front are a couple weak lows, and biggest lows being right here. You can see a warm front coming out to the east from this low. So we have here a whole bunch of moisture coming up this way, warm air. From the other direction, we have cold air coming in. Matter of fact, temperatures are in the 30s in the Dakotas right now, so there is strong cold air advection on the other side. So along that front, then, there is a stark boundary. This warm air is trying to lift to the north. Cold air sinking south. What happens is we have a very steep slope. So the air is being forced to rise pretty drastically. That would be wonderful if we had no instability. If we had a nice stable atmosphere, we would get decent rain showers, but we would never get a thunderstorm. However, we don't. Instead, we're going to have very significant instability up here. And I wanted to show you that by looking at something here. This is an afternoon sounding out of northern Oklahoma. Bottom layer getting pretty humid, lots of moisture right here. Above that, however, notice this very warm layer. So anything that rises from down here at this point, if it was pure convection, no lift of a front, would hit this, hit stable air, and go right back down. However, we don't have that. So what we're doing is we're pushing a cold front into this area here. And instead of just stopping right here, we're pushing this air as well upwards. It reaches saturation pretty quickly. You can see it's already saturated here. So as this erodes, this is your instability. This is the actual temperature curve that a parcel of air will take as it's going up. Notice, on the other hand, where the atmosphere's temperature curve is, way over here. So we said air was unstable and accelerating upward when it's warmer than the surrounding atmosphere. Well, another thing that's going on, we're going to be pushing moisture into this area right here. So what's going to happen to this temperature and these dew points, they're going to converge. We're actually going to get cooling in this part of the atmosphere as well. So we wind up with a very, very unstable atmosphere here. Atmosphere parcels are going to shoot upwards very quickly. So they're going to go up high and they're going to generate thunderstorms when they do that. This is just a classic afternoon sounding of the potential for severe weather. The fact that it was warm down here kept any big clouds from starting to pop up early. You allowed the temperature to warm as much as possible. It's almost 30 degrees Celsius down here. Probably even got warmer than that. All of that allowed thunderstorms to develop. Thunderstorms basically, when they go up, have two components. The first initial stage is of all the air is rising. Eventually, they reach a point where some of the air starts coming back down, and that's where the precipitation begins. The precipitation gets heavier and heavier. The air gets cooler in that where the precipitation is, so you wind up with it dropping back down towards Earth due to gravity. So when it does, you get a circulation that has air going up and air coming down next to it. That's a mature thunderstorm. Eventually, all the air will be coming down, and that's when the thunderstorm's dying. So if you have an individual thunderstorm cell, it's not maintaining itself real well. Typical summertime, you'll have part of the air going up, part of the air coming down, and eventually all the air will be coming down and the thunderstorm will be dissipating. Typically can last anywhere from a half hour to an hour. That's it. That's as long as they go. Now, thunderstorms can work in groups. Let's take a look at a group of thunderstorms right now, as a matter of fact, what's going on. This is a ghost satellite imagery with lightning. Notice all the lightning along that front right now, all the way up. So what you're seeing here with this is these thunderstorms have organized into a line or a cluster. They're actually feeding each other. In other words, you'll find new ones developing to the south, moving north. They'll be gradually dissipating. And by that time, another new one will have developed down to the south, moving north, and continually moving the line slowly to the east and south with time. So that is what is happening with these thunderstorms. Ghost satellite imagery, since we got the lightning detection, has been great. The more red you see, the heavier the precipitation and the higher the thunderstorm is. So what causes lightning? Let's talk a little bit about that as well. All right. Interestingly, in a thunderstorm, when you have the air going up, you're going to you have a very warm air rising. It's eventually going to hit temperatures that are well below freezing, but it's going to be above freezing. And gradually it's going to shift, and some of it's going to become ice. Interestingly, ice changes charge at around minus 10 degrees Celsius. So below that, it's one charge. Above that, it's a separate charge. So that difference in charging allows the lightning to form. It's trying to get rid of that two different polarities. So that is how your lightning develops in these storms as well. You can see some lightning down over Florida as well. And along that warm front, plenty of thunderstorms there. Matter of fact, there's some flooding going on in Ohio right now. So now that we've seen this on upper levels and we've talked about these storms, let's look at the radar for a minute. Here's your heavier precipitation. The reds into the purples even are the heavier precipitation. So, and that's where the thunderstorms are, right along that line. This is Kansas City here. So just to the west of Kansas City is a whole line of thunderstorms. Other ones out towards Topeka. Say I wanted to look at radar is a very useful tool. One of the things it can allow me to do is look at velocity. So that changes. And interestingly, everything's from southwest to northeast. Notice right here becomes zero or almost no velocity. That is because that is parallel to the way the parcel is moving. Doppler doesn't pick up a velocity when it's like that. So here you can see you have winds are moving towards the radar. Here they're moving away from the radar. Now, if you looked at individual cells and found rotation, which can show up, it doesn't show up really right here right now that well on any of these. It's a little bit of possible rotation because there's a little weakness right in here. But other than that, these look like very straightforward, typical thunderstorms. As a matter of fact, I'm seeing this here is probably an outflow that pushed out of these thunderstorms a long time ago. So that would be the cold air that comes down from the outflow that hits the ground and moves out ahead of them. So now we're back to this sounding again. I wanted to show you another thing. We've talked about wind shear and how it influences what type of storm develops. Well, when you have wind shear, what you're doing is maintaining the updraft in a vertical way, allowing warm air to come up over that cold air that you just saw me pointing out and lift and still be lifted back into the thunderstorm. The further ahead that outflow boundary gets, the less warm air can get into the thunderstorm and the better chance it's going to die. So with wind shear, the stronger the wind shear changing direction or increasing in speed with height, the better chance that outflow doesn't go very far out in front and the thunderstorms get calmer. Right now, it doesn't look that great there. So you can see here, we start off with a southerly wind, then it shifts to southwest at 40 knots. It really is pretty uniform wind shear. The winds are just gradually getting stronger with height to here, and they stay about the same all the way up. So this is not a fabulous sounding as far as wind shear goes. I might be able to look a little further north and see something better. I don't know. Let's take a peek. So yeah, there's good southerly wind here at the bottom, but then it shifts to the southwest, and it does get stronger with height up to about 8,000 feet. But again, it's not something spectacular. Uh, we can use a lot of tools, however, when we're forecasting thunderstorms. And here is that line of thunderstorms. Cold front is right in here. You can see the southerly winds here, northwest winds here, good convergence along that front. So if you wanted to know some stuff about this, this is all available on the Storm Prediction Center's website. I am not going to try to show you the over 100 and some different fields that are here, but I wanted to look at a couple things. We talk about convergence of wind. Well, there's also convergence of moisture. Think about it as warm air coming up, moist warm air. It's cold air coming in. You're converging the winds, but if you're pulling in moisture into that same section, you're converging moisture. We have learned through the years that thunderstorms like to develop where moisture convergence is maximized. Well, look at this. Really, really good correlation here. Very strong moisture convergence. Excellent thunderstorm development in this area as well. So that first parameter we just showed you works really well here. You can even see it up in this area as well. One of the interesting things is you'll notice with time, when you're watching thunderstorms sometimes, you'll watch the moisture convergence begin to die out as it moves east. When that happens, thunderstorms begin to weaken. Another aspect of this we could look at would be in the upper air if I wanted to see, oh, how much deep moisture do we have? And you can see here, there's some pretty deep moisture coming in. So that means it's going through several layers. It's not just near the surface. That's what's keeping these thunderstorms going as they're moving east. If I wanted to look at Cape, all Cape is, when I showed you that, what the temperature would be in the parcel being lifted, think about that difference, that area that's between where the actual environment temperature is and the parcel temperature. The bigger that area, the more unstable the air. That's Cape. And right here is where the maximum capes are. Generally running about 2,500, a little over 2,000 here. On the other side of this, no cape, no instability. So this is not very huge by any stretch. Huge would be up to 3,000 to 5,000. Some of the worst tornadoes have occurred at 4,000 to 5,000 cape. So this is a significant thunderstorm event, but it's not really something that all the news outlets are probably going to pick up on tomorrow. There'll be some minor damage maybe from these thunderstorms, but probably nothing massive. Finally, looking at wind shear, we take wind shear from surface to 6 kilometers, and I'm looking for 40 knots of wind shear for severe weather, typically at least. And we can see right along this is where actually the 40 knot line is. So it's barely into it. Now back in the stable there's some pretty strong winds here, 70, 80 knots. So again, it's a decent field. It's not a great wow field that's going to say, I'm going to have a lot of severe weather tonight. We are having thunderstorms and we are going to have rain with them. That's moving east with it, but it's not something that I would want to be fearful of major tornadoes breaking out. And as a matter of fact, while they have tornado watches out there, they're indicating that they're only expecting isolated tornadoes with them. So this is taking everything you're going to be learning this week and applying it to a weather event today, right now, so you can see how it works, how you can utilize what you're going to be learning about. So if you have any questions about it all, please don't hesitate to ask.